Alright, hello everyone. In this video, I'm going to go over determinant as area or volume. So we'll see determinant, the meaning of determinant in a view of geometrical aspect. So let's take a look at the 2 by 2 matrix, diagonal matrix A. And then when you see when you consider each column vector as the vector a1 and a2 and draw these vector on the x1 x2 axis. Okay, so now here this is a1 and this is a2, and then let's find out determinant a. I mean the absolute value of determinant a. Then the absolute value of determinant a is going to be x1 times x2 right? Because in 2 by 2 matrix, determinant, the formula of determinant is what? A b minus bc, right? A times b minus b times c. So absolute value of determinant a is nothing but the absolute value of x11 times x22. This is exactly same as the area of that rectangle shaded by the yellow, right? Yellow, color yellow. So and then yeah, so now here for the any diagonal 2 by 2 diagonal matrix, determinant of matrix absolute value of determinant a means the area of that rectangle, right? Now, next one. What about the non-diagonal matrix? I mean, just arbitrarily 2 by 2 matrix, say A tilde. Then there exists the here. This means that there exists A tilde, which is this, such that determinant of absolute value of determinant A tilde is equal to absolute value of determinant of matrix, diagonal matrix, which means that for any 2 by 2 matrix A, actually, okay, can be transformed into a diagonal matrix. So this is any 2 by 2 matrix, should be A tilde, okay, it's typo. A tilde can be transformed into a diagonal matrix A in a way that changes neither the area of the associated parallelogram nor absolute determinant A. So what that means, the any 2 by 2 matrix A tilde can be transformed to the diagonal matrix, but the that transformation will not affect on the area of the associated parallelogram nor absolute value of determinant A. So okay, that's okay. So here, then why here we mentioned the associated parallelogram, area of the associated parallelogram. Just take a look at this. Actually, the in conclusion, the absolute value determinant A tilde that represent the area of that parallelograms, and then this is the obtained by the two vectors. See the two vectors right here? These vectors are the column vectors of A tilde. Okay, so considering each column in A tilde, each column in A tilde as the vector in x, and then draw them in x1, x2 axis. Okay, then we get the we can draw the parallelograms. Then the area of the parallelogram is nothing but absolute value of determinant A tilde. How come? Okay, here. So let's say matrix 3 by 3 matrix B is like this. So you see that A11, A12 through the A22. These are matrix A, arbitrary matrix A. Okay, we can say this is A tilde. Okay, and then we so and then the third diagonal entry is 1, and then all other entries in a third row and third column is 0. Okay, so now then the area of parallelograms is the absolute value of the cross product of A1 and A2. It makes sense, right? Because I believe that you learn in vector calculus. So then A1, and then because A1 is because all third and the components in a vector A1 and A2 is 0. So vector A1 and A2 must be on an xy plane, x1 and x2 plane, or you can say that. So then the area parallelogram must be this, right? Why? Because see that here, and then why this is related to the determinant of the matrix A. You see. So let me calculate the compute the cross product of A1, A2. Then this will be the absolute value of determinant of the that matrix. This is how we calculate the cross product, right? So now then that's gonna be what we just pick what using applying the cofactor expansion, right? For finding the determinant, then we get this because these two entry at 0, so we're gonna get this one left. That determinant will be left over. Right? Then that is equal to determinant of the A transpose, but determinant A transpose is equal to determinant of A. Okay, so now you see that the absolute value cross product, I mean the magnitude of the cross product is equal to absolute value of the determinant A, right? You see that? That's why the area parallelogram is equal to the absolute value of determinant A. Okay, so now then for any the matrix A, or you can say A tilde, the determinant of that matrix A or A tilde is equal to the area of that parallelogram, right, constructed by the column vectors of matrix A or A tilde, either one is fine. Then that one, then there you could just the matrix, I mean the diagonal matrix A. I mean, we can transform the matrix A to the diagonal matrix, okay, and then the so that the area of this one, the square, sorry, rectangle, is equal to area of the parallelogram. Okay, so now that's why the determinant A, when A is 2 by 2 matrix, determinant A is going to be area of the rectangle. Okay, so and then so we can easily find out compute the determinant A by finding area of that rectangle. Okay, so actually this is what I mean. How can you find out the diagonal matrix? The such that determinant A is equal to determinant of the A tilde. We just do reduced row echelon form, right? When you apply the reduced row echelon form, then you can find that this one can be transformed this, right? So it's not a big deal. So now then, what about the 3 by 3 matrix? Okay, so now determinant of the 3 by 3 matrix is actually volume. Okay, after we determine A is volume. So any 3 by 3 matrix A can be transformed into a diagonal matrix using column operations. Okay, we use this one when you do the what when you reduce when you get the reduced row echelon form or reduced row echelon form. Okay, that do not change absolute value of determinant A. So it means that these operations do not affect the volume of the parallel pipe determined by the columns of matrix A. Yep. So any the row operations or column operations, uh, these these will not effect on the volume of parallel pipe determined by the columns of A. So in 3 by 3 matrix, since the 3 by 3 matrix has the 3 columns, then draw the column vectors on space 3 by 3-dimensional space. Then we're going to get the see the A1 and A1, A1, A2, A3. So then when you construct the some solid using A1, A2, A3, we're going to get parallel piped, right? So then the volume of parallel pipe, that's the absolute value determinant A. Okay, so why? Because let A be A1, A2, A3. A1, A2, A3 are columns of 3 by 3 matrix. Then there you go, just the B and C. I mean, real number B and C, such that determine A absolute value is equal to absolute value of determinant A1, A2, and this A3 plus B, A1 plus C times A2. So what that means? It means that the the uh, the we can we can the applying the row operations or column operations. So this one can be transformed to the diagonal matrix. That's the reduced row operation form. Reduced echelon form. Okay, sorry, reduced echelon form. Then what's the determinant of the matrix D? It was D1 times D2 times D3, right? So absolute value of D1, D2, D3 must be equal to absolute value of determinant A. So, but what is this? This is what? This is volume of pellet pipe, right? So the determinant of matrix A is nothing but volume of pellet pipe. Okay, so in this video, so we could figure out that, okay, determinant 2 by 2 matrix, what area parallelogram, right? And then for 3 by 3 matrix, after you determine A, represent what? Volume of pellet pipe. Okay, so that's for today.